Data Skeptic features interviews with experts on topics related to data science, all through the eye of scientific skepticism.
Jon Morra has a PhD in biomedical engineering. He has founded two companies, the OnCode Group, which builds web applications, and Medical Vision Systems, which applies machine learning and computer vision to the medical domain. He is presently the Director of Data Science at eHarmony. Jon, welcome to Data Skeptic.
Hi, thanks for having me.
I'm glad to have the chance to talk to you about some of the data science and machine learning work going on at eHarmony. I enjoyed your talk when we both presented at the LA CTO's forum a little while back, and I thought it'd be interesting to share some of your insights with my listeners. One of the things I've always been curious about in the online dating space is how you successfully blend machine learning approaches and other approaches. Presumably there's a line somewhere between what you can solve in terms of matchmaking algorithmically and what is more soft skills or something along those lines.
So I don't know if I necessarily agree with that. I think that the notion of love is potentially quantifiable. I don't want to say it definitely is, but we take the approach that we can have a high success rate by matching people on both compatibility and on what we call affinity. A quick overview of how that works is compatibility is this notion of long-term attraction. So eHarmony was founded on this idea that if you find somebody who you're compatible with, you're going to have a successful relationship, you're going to have a successful marriage, you're going to be happy 5, 10, 15 years down the line. Our psychologists, we employ a team of psychologists, go out and do what's called factor analysis to extract personality factors and match people on those personality factors. And we know, because our psychologists have experience in marriage and family therapy, that when individuals are matched on these factors, they have happy long-term marriages. So we know that when you get matched, you're the same on sexuality or romanticism or whatever, then you're more likely to be happy in the long term. But eHarmony also wants you to be happy in the short term. So that is affinity. My team does a lot with affinity matching. We define affinity as 7-day two-way communication. So if a match is given out between two users, user A reaches out to user B and asks a question, user B responds, we consider that a successful match. We use compatibility as a threshold. We only deliver matches if you have a greater than 75% chance of being happier than marriages in the wild. So we've gone out and studied marriages in the wild, and if you're in the top quartile, you could be matched. And then we also seek to match you with those people that you're going to have that quick, short-term spark with as well.
When it comes to compatibility, is there an overlap in the features you look at, or are you taking some of the data sets that those psychologists are gathering?
We have looked at it in the past, and it turns out that who you like and who you love are divergent populations. If you've ever signed up for a site, we ask you a kind of lengthy relationship questionnaire, and we've played around with using those in Affinity, and it turns out that it doesn't affect Affinity that much. It's really important for compatibility. And I'm sure that, I don't know if you have, but I know I have, and other people have had this experience where you meet somebody out, you think they're great, they're very attractive, and you get to know them, and you don't click with them. And the inverse as well, where you find somebody you're like, I don't like them at all. You meet them 4 or 5 times, and you start to develop an attraction to them.
So is compatibility in your guys' pipeline sort of the deterministic first step where you just high level trying to eliminate all the false negatives and then do some affinity analysis?
That's exactly right. So we have 3 stages to our matching. Compatibility is first, where we take our full n-squared problem, which is in the trillions, and narrow it down to a set of pairings. Pairings satisfy 2 criteria. 1, they're psychologically compatible. 2, they meet each other's self-selects. So self-selects are things that you say on the site, like I only want users within this distance, with this ethnicity, with this religion, whatever it is you say. That becomes pairings. Out of the pairings, we score them for affinity. So this is the probability of communication. And then from that, we use a graph flow optimization where we put men on one side and women on the other side of a bipartite graph. We have edges from the source and the sink to all the men and the women. The interior edges are the pairings. The cost of the interior edges is minus the affinity score. And then we have some constraints on the exterior edges for the number of matches we want to give you each day. We solve this using a graph solver, specifically CS2, and out drops a number of internal edges, and what you're left with are matches that are delivered.
Very cool. I would definitely want to talk more about the graph flow problem, but had one more kind of follow-up question to how you guys have designed this. As you'd mentioned, you're optimizing for successful long-term relationships, which I think is a very admirable goal. It's not necessarily the only goal. You could optimize for short-term relationships for some reason. I guess the way that you're expressing that objective function in the affinity scoring is that 7-day two-way communication. Could you talk a little bit about how you arrived at that? Why not 8-day communication or depth of conversation? What made that the best objective function for you?
When we look at the data on our site, we notice a lot of our users are highly cyclical in their behavior. So they log in just on the weekends, or they look at it just Wednesday night or whatever. So we found that 7 days was the minimum unit of time to catch these weekly cyclic behaviors. And by going more, we just had to wait longer to validate the efficacy of any model we deployed. So we wanted to choose the smallest unit of time such that we can catch these cyclic behaviors.
Makes sense. And let's get back to that graph flow problem, maybe first from sort of a computational theory perspective. Why is that a practical approach that you can solve with the technology you have?
The naive approach, if you take a step back before, I'm not really sure exactly when we implemented the graph problem. It was before I was hired here. But the naive approach is a round-robin approach. So in a round-robin approach, you pick one person and deliver their best matches. Then you pick another person and deliver their best matches, and so on. The problem becomes that we have some constraints, and that is the number of matches we want to deliver you each day. So if you're at the bottom of that round robin list, you have a bad experience. And we saw this. A lot of our customer complaints in the early days could be directly attributed to the depth of where you were in that list. So by doing a graph flow optimization, we have a much more socialistic approach that says, we're going to jointly optimize for everybody at the same time.
So would it be correct to interpret that as saying that if, I don't know how it was done when it was round robin, but let's just assume oldest customer first, that the most universal or best matches are automatically found for those first customers, and then as you get to the end of the list, it's the less appropriate matches, maybe is a way to put it?
Well, the less affinable. So this idea that you're competing with people on the site for certain matches, you're going to be matched with the same people, right? And some people are highly desirable on the site. You can get pairings with a lot of people. When we have the round robin approach, you will lose if you're not at the top of the list, right? Because that person's matches will be filled up when it's your turn to get matched. So they're not available to you. So you will have less desirable matches for you.
Yeah, eHarmony has sort of a difficult position to be in there in that you have a large number of customers and you want to take all their best interests in mind. So this seems like a great middle ground for satisfying sort of a global problem with respect to the competition amongst everyone in the possible pool. Could you talk about the process of how you guys evolved to that solution? Were there any key lessons learned along the way that made this the right step for your implementation?
So I will say that I was not here at the time that was done, but my understanding of what happened was that we brought in a mathematician whose name escapes me at this point. I was told it probably a couple of years ago, and I'm not really sure who it is, but he suggested solving this problem as a graph optimization because it was computationally tractable and it fit really well. So this kind of approach is really prevalent in a lot of delivery businesses. Like if you were to go to like FedEx or something, you could see this graph flow optimization is huge money for them because they're transporting goods from point A to point B subject to some constraints. Historically, that's really all the information I have.
Let's talk a little more about Affinity. I presume that everyone is represented in some feature space, and then you're finding a similarity between my vector and my potential matches. Is that more or less the approach?
So that is one approach, but that's not the approach that we take. So you can cast this as a recommendations problem and solve it, by minimizing some cosine similarity or something like that. We actually do it as a dyadic classification problem. We extract features from the man and the woman, and then the target variable is whether or not they communicated. This is for historical data. So we actually solve it as a fully supervised classification problem, binary classification problem.
You'd mentioned extracting features from men and women separately. Are there different features that represent each gender more appropriately in your problem?
So in our problem, no. Our feature list is pretty deterministic and not really gender specific. Obviously, the actual values you get are gender specific, but the features themselves are the same on the men and the women.
I would also suspect that a lot of users are doing their best, I won't call it lying, but to present themselves in the most positive light, maybe a photo that's a little lighter in weight than I am today, things like that. Does that imprecision of observations hinder your efforts to make good affinity matches?
That's a really tough question to answer. On one hand, you would say it does. On the other hand, we've done analysis that basically shows it just so happens that every user on our site is 3 inches taller than the national average.
Interesting.
Take that for what you want. You could argue that yes, people do it, but it kind of evens itself out, if everybody does it. So I'm not saying that definitely do not lie. I'm not advocating for that at all, but I don't think you need to specifically detect these kinds of, hey, your picture doesn't look exactly like you, or, your height's a little wrong. Now, we certainly do have outlier detection. So if you are way out of the norms of what we expect, we do have a team that will investigate that profile personally and say, you know what, it says here you're 7 feet tall. The probability of anybody being 7 feet tall is very small. Can we, have some verification? And then if it turns out you're 7 feet tall, then that's perfectly fine.
If I understand correctly, it would be fair to say you're really trying to predict that communication will occur if a match is suggested. Is that a sparse problem? Do you have an imbalanced set that communication is rare? Or is that taken care of just by the very fact that you're optimizing for communication?
We do have a class imbalance problem. A lot of it comes from the fact that we deliver matches at least every day, sometimes multiple times a day. The most important feature in our affinity models are login probabilities. Right? If you haven't logged in the last week, by definition, you can't communicate. So we do have a class imbalance problem, and we're actually just about to release a solution to that. It's kind of fortuitous timing. So this is something that we observed in some holdout data that we tried and just our European customers, and it proved to be very successful. So what we did is we noticed that the probability of communication is less than other definitions, potential definitions of affinity. Right? At the end of the day, affinity is not necessarily 7-day two-way communication. It's more abstractly, do you like this person? So you could choose to define that differently. My team and I thought that, maybe another definition we want to try with is just simple profile view. So maybe the act of just viewing, which is a prerequisite for communication, might help us in this problem. And it turns out that the probability of being viewed is significantly higher than the probability of calming. So what we did was we actually trained models on profile view, but then evaluated them on the same KPI, 7-day two-way calm, and they were significantly better. Now, this is very interesting for me because we just optimized on something that we're not measuring, yet we're doing a lot better. So I've thought about this a lot. How is this possible? And I think the reason is because the amount of effective data we have is so much greater in profile view. So even though we're not directly optimizing for calm, the problem space is bigger because even though we have many millions of points potentially to train on, your data set's really only as big as your smallest class effectively. So if you can make your smallest class bigger, all of a sudden the statistical power in your models increases potentially dramatically. When I saw this was like a big eye-opener for me because I did not expect this result at all. I was prepared to go and advocate why I thought profile view was more important as an affinity measure, and I don't have to do that at all. We're just significantly better now at two-way calm.
Yeah, the proof is in the pudding. Very interesting. You said something particularly novel that I think is a good lesson for people who don't know necessarily that much about machine learning, that your most predictive feature of communication was login probability, which sounds maybe to a business user almost frustrating. Like you're telling me that the most likely chance that someone's going to talk is if they log into the website, which is a prerequisite for talking. And it's sort of one of those variables that has great explanatory power, which is required to sort of account for maybe the uncontrollable aspects of the model. And after that, you can get into perhaps some of the more interesting controllable values. Do you guys look at it the same way, or am I kind of imposing my own perspective on that?
No, we actually have considered making a separate login model and then using that as a conditional prior upon an affinity model. That's certainly a research project that is on our plate to do, but in that case, yes, you could imagine taking a cascading type approach where you could say, look, I'm going to use a login model as either a threshold or a prior, or whatever you like, and only train for compatibility for those users that passed, where I'm using air quotes to say whatever that means, past the login model. Like their probability of login is above a certain threshold. So therefore, you allow your affinity model to focus on those users that are more difficult to classify. So this is actually a page taken out of like a Viola Jones book. So if you ever read Viola Jones's seminal paper on facial recognition, this is very similar to the approach they used where they had cascading classifiers to detect facial analysis. And the idea was that as you went deeper in the classifier, you rejected those easy to segment regions of the image, and you allowed deeper classifiers to focus on more difficult examples. So this would be kind of analogous to that.
Yeah, while we're on the topic of the role images can play in this, I'm curious how you guys are leveraging photos in your feature space. If I were starting on dating, day one, build it from scratch, I'd start with easier things like the survey questions that are very deterministic, and I can build very simple classifiers on them. But of course, there's a very intuitive, appealing opportunity here that the image can be very information-rich in what people will like about each other, but also very challenging in the vision problems. How prevalent is computer vision in your guys' affinity process?
So we definitely have a lot of computer vision. I mean, we have essentially two big sources of unstructured data, free text and images. And they can potentially say a lot. So specifically in the image space, I have written and actually open sourced a facial recognition algorithm that we use here called FaceBards. It's based on a paper that was published by UCI in CVPR 2012, and it's a C++ web service that will accept the JPEG and then return back JSON that says where every face in the image is, and 68 fiducial points on an image for a frontal face and 39 fiducial points for a profile face. One of the insights into our image data, and this isn't that surprising, is that almost all of our images contain a face. So doing facial recognition is a reasonable place to start. And so some of the features that we extract from the image are going to be simple features like your aspect ratio, which obviously requires no face, your face ratio, which is the area of your face divided by the area of the image. You can think of it as a zoom factor. And we've done a lot of analysis on that particular feature and found that it's actually very predictive. There's a very specific range that people want to see. Too close and you see see too much. Too far away, you don't see enough. Then we have a number of Boolean features that extract from your face. Do you have a beard? Do you have a mustache? Are you wearing sunglasses? Are you showing cleavage, which everyone loves? And these are all features that kind of allow us to understand what it is you prefer. I also extract your hair color, your eye color, and I extract your BMI from your image as well.
Oh, really? That's very interesting.
Yeah, so that one is based on another paper I found by a group out of West Virginia University in 2013. It was actually published in a psychological journal where they had a bunch of subjects that were taken where they had laboratory condition images, so perfect lighting, background, no facial expression. For all these individuals, they had their BMI. They used OpenCV to extract various markers on the face and then created a number of measurements, various ratios of different measurements on your face, and then used that in a support vector machine to regress the BMI. Now, at eHarmony, we don't ask you your weight. Our customers have made it very clear that they don't want that, yet it would be naive to say that weight's not important when you're choosing a mate. Obviously it is. So knowing your weight is important. So if we know your height, which we ask you, we know your BMI, we know your weight. So I really wanted to go and directly assess your BMI. In order to do that, I need ground truth. I asked the West Virginia guys for their data. Unfortunately, I couldn't get it. But at the end of the day, it doesn't really matter. If I can provably extract the same components of the BMI that they do, that is not only sufficient and may be superior because these are going to be individual features that are fed into a subsequent machine learning algorithm. So actually knowing your raw BMI is not necessary. We know the components of your BMI.
You'd mentioned face parts. A couple of questions there, actually. Those 58 fiducial points, are those things that I could recognize? Are those like the ratios you were mentioning of like face height to weight? Or is it...
No. So fiducial markers are points in an image, not necessarily a face, that don't change regardless of image conditions. So for instance, the tip of your nose is the tip of your nose regardless of if it's occluded, if the lighting changes, if it's a different position in the image, it's still the tip of your nose. Those are fiducial markers. So we'll have fiducial markers around the chin, around the mouth, the nose, and the eyes. And so the whole idea is that, point 38 is always in the middle of your left eye. So anytime you can essentially assign a mapping from a numeric fiducial marker to a specific textual description of what it's supposed to be.
When I started looking into vision, it was some time ago, and my assessment was that AdaBoost was the sort of leading approach. And now, of course, we're having deep learning showing a lot of successful places. And it seems like we're in kind of a renaissance of this space. How has that renaissance, if you agree that it's going on, been affecting you guys?
Funny you should mention AdaBoost. My PhD was an extension to AdaBoost that we developed at UCLA that used neighborhood-based features to do image segmentation in the medical domain. So I am very familiar with those kinds of approaches, but the deep learning stuff has just proven so much more effective. We're not yet employing deep learning here. It is very high on my roadmap. I've been playing around with various packages, Torch, Theano, Cafe, TensorFlow, you name it, I've probably touched it. And it's certainly the next step. The problem that we have is that none of the off-the-shelf classifiers for deep learning and image processing make sense for us. We have to train our own. The real problem is that if you look at something that was trained on ImageNet, they might have 1,000 classes or a few thousand classes that they're looking for, but our images are always of people. So if you were to just take Cafe's off-the-shelf ImageNet classifier and throw our images at it, which I've done, you get back the same answer. There's a person and they're wearing clothes. While not incorrect in any sense, totally correct, but not useful. I want to know there's a person and they're at a baseball game, or there's a person and they're at the club, or there's a person and they're skiing, or whatever the case may be. That's the useful information, not the fact that there's a person.
Yeah, that seems to be one of the biggest overheads. I mean, set aside the fact that we've got to get all the GPU servers set up, just the raw training and labeled data set. These things seem to require massive amounts of training data.
They absolutely do. And so that's something that we would have to look at, probably like a Mechanical Turk type solution when we go that route, which is, like I said, is very high on our roadmap.
So you guys are clearly using and exploring lots of different cutting edge technologies and proven methods. One technology that I believe eHarmony makes pretty good use of, or at least has in the past, is Vopal Wabbit. Could you tell us a little bit about what VW actually is?
VW is an exceptionally fast linear learner written by Jon Langford, who actually sits on our scientific advisory board. Jon Langford is a researcher formerly at Yahoo, now at Microsoft. He's actually the general chair of ICML this year, for anyone going. I think that VW is probably the fastest learner in the world. I mean, it tears through gigabytes of data in seconds on one machine. It's very, very, very good at what it does, but it's not a nonlinear learner. Now, it has a lot of the ability to do quadratic interactions and high-order interactions, polynomial type kernels. It's also only online, so it only implements online algorithms. Recently, it's implemented a variant of online SVMs for a linear kernel. It's implemented bagging with Poisson sampling for online bagging. It's done online boosting, but it's a very, very good online learner. Historically, my predecessor's predecessor used VW, and it's been at the company since 2008. We're very tightly integrated today. And actually, the biggest use of it today is not only as a fully supervised learner, but also as a contextual bandit learner. So we make use of contextual bandits here a lot, and it's growing right now. And VW has one of the only open source implementations of contextual bandit style learning that I found. So we use it for that a lot.
Interesting. How do bandit problems fit into your workflow?
So bandit problems fit in all over the place. So the idea, a brief overview of what bandit problems are, is that it's a semi-supervised learning approach where what you have is a tuple 4 at train time. You have a context, an action, a reward, and a probability. Your context is analogous to your feature set in fully supervised learning. Your action is something that is chosen by the system. So, for instance, we make use of bandits when we're doing some A/B testing. So on the site, we might have a couple of experiences that we want to show a user. So instead of doing a more traditional A/B testing approach, where you would divide your users up into set group A and group B, give them the two experiences, see which group performed better, where that's whatever that means, and then choose one experience as the winner, you could actually choose both experiences and give them out to the users. Those would be your actions, which experience. And then your reward is some measure of success. So a reward might be, did the user log in? Did the user communicate? Did the user purchase? Did the user take any action that we think is positive for the business? And then we also need the probability with which that action occurred, and we record that at trade time. So the reason that it's a semi-supervised learning approach is because you don't know what would have happened if you would have given the user a different action. So we gave you experience A, you gave us this reward, maybe nothing, maybe something. But if we had given you experience B, we don't know if you would have given us a bigger reward, a smaller reward, whatever the case may be. You really need more training data. Naively, you can think of it as N different supervised learning, fully supervised learning problems, where N is the cardinality, the number of actions you have. So you could naively think that you need N times whatever you would need for one supervised learner. So you need more data to do this. But it's proven exceptionally effective here. Like I said, within product, for A/B testing various experiences. We've done it on email campaigns to say what hour of the day to send an email. And we're just exploring it in a bunch of different domains. It's proven exceptionally successful.
We've touched on so many things. I could imagine where you've got an enormous feature space to potentially look at when you're trying to predict the communication will take place. Do you guys end up applying any sort of regularization to dampen the magnitude of some of those features or to reduce the feature set? I could see where maybe there'd be a business constraint that they don't want to have too many possible variables used for prediction. What's your guys' best case solution?
So we have played around with regularization, both L1 and L2, and in our case, it hasn't proven effective. We're pretty lucky that the business folks kind of let us do our thing, but we're purely data driven, and it just hasn't proven that effective. Now we have done feature exploration to remove collinear features. That certainly has proven effective. But as far as just applying L1 and L2 regularization within Affinity, the data just says not to do it.
Makes sense, yeah. Are there any features you guys have found that were counterintuitively either helpful or unhelpful? Something that sort of surprised you as you work through it?
I haven't found anything that's been that counterintuitive in the Affinity problem. We find that the most important features are login-based features and historical activity. So are you somebody that likes to talk? Are you somebody that not likes to talk? Are you somebody that's very active on the site? Those are usually the most important. Also important are similar features. So features like, are the men and women the same religion? Right, that's an important feature. Those kinds of things. So, no, not really. Like most of it has been pretty explainable.
Yeah, that's. I bring my own bias to the table here, but I always find that while machine learning is very powerful, rarely is it spectacular in some unprecedented way. Like if you came in and said the secret is you have to pair people that like bowling with people who've been skydiving precisely twice. You've either overfit your data or you're talking about some very subsample that's of questionable state anyways.
And we actually had that recently. I did an experiment where I was using bandit learning to determine the optimal number of matches to deliver to each person each day. We did some subset of random sampling in order to get some training data. Trained a bandit learner, so there were, I think we could deliver 6, 7, 8, 9, 10, or 11 matches. We optimized for the total comms you had. So you would think that naively more is better, but that's not necessarily true because of the paradox of choice. But at the end of the day, we made a model that worked significantly better than what we were doing. And when we investigated it, there was essentially 2 spikes in the actions chosen by the learner, one at the low end and one at the high end. And when you looked at the model, the highest weighted features by far were how many people had you talked to in the last day, 2 days, 3 days, and so on. And it kind of come back to your point. It's like, yes, that is what you would expect to be. If you want to chat, we want to give you more people. If you don't want to chat, we want to give you less people. But at the same time, the machine has learned this. And the nice thing about machine learning is that you don't have to design any business rules. And if you have an automated training pipeline like we do, then if people's desires change over time, which they do, you'll just capture that automatically and push it out right into production.
So thinking about that optimization for communication, it occurs to me, if I were someone who was willing to commit, 10, 12 hours a day to go on your site and respond to literally every message I got and contact every person I possibly could, now, there's no guarantee that's going to be two-way, but I'm almost like a spam agent at that point. Do you have to worry about cleaning people like that out or balancing for it? Or is it that the nature of someone who's emitting such a high volume of messages is of low quality and getting low response anyways?
So like you said, a lot of those people don't get a lot of two-way communication, but we do control for that. So we look for people who communicate with a certain percentage of their matches, a very high percentage, and exclude them from training because we assume they're not acting in the way the system was designed, which is for you to consider matches and then communicate with those that you like and don't communicate with those that you don't like. So essentially, they provide no value at train time.
eHarmony has obviously successfully matched a huge number of people who are in, long-term relationships and marriages and whatnot. Yet we've touched on a couple of points of open, interesting R&D. How do you guys know, I think earlier you said you can't be done, but I recall seeing someone from Amazon's recommendation system team that joked, Amazon's recommender will be finished when the homepage of Amazon is one product that you immediately buy.
So yes, you could make the same argument at eHarmony that eHarmony is done when we send you one match and you immediately leave our site because you found the love of your life. The problem with that is that when you're on Amazon, you are looking for something. You probably have a desire to make a purchase. When you're on eHarmony, you could say that you have a desire to find love, but your response with the system is going to be much less deterministic, if you will. You might not come on the site because you're nervous, because you don't know what to say, because you had a bad day at work and you don't feel like dealing with, romantic relationships right now. Totally external to eHarmony could still provide you perfect matches, and they might not work because you're not in the right place emotionally or whatever to be able to communicate with that person. So I kind of think that you can't ever design a scenario where you're done, and it's not because it's not possible, although it's probably not possible. But even if it was possible, it wouldn't be because of the nature of the business.
One of the things that resonated with me, and maybe I'm reading into it a little bit, but in your LACTO forum talk was how the system is tunable for the desired number of matches per day. And while that in and of itself could be a data science problem, what's our objective function? How do we optimize this? What I heard was maybe a situation where this is a control system the business wants to have management of, that there's a VP of something or other who wants to be able to fine-tune that. And there's a delicate balance between what a business should control and what a data scientist should control. And it sounds like you guys have had the liberty to do good research and produce good solutions. How do you strike that balance?
Yeah, it's always a tricky subject in any kind of data science environment, is you frequently have to manage up. And we've done that. And since data science has existed at eHarmony since 2008, we have the luxury of having a long-term track record of success. But there's still, when we want to break into new endeavors, like deciding to change A/B testing, that's scary to management. And the way that we've approached it successfully is that we will take small subsets of people and say, look, we can afford to make mistakes with these people. So if we've been successful before, if our trained model on this small group of people is not successful, then okay, we didn't do our jobs. That has yet to be the case. And so our management has been very good at allowing us the room and the time, really the time is the more important thing, to experiment. And we're very transparent that at training time, when we're exploring what we might do, we're going to be worse potentially. And that's the cost of doing business, so that in the future, we're going to be significantly better. And that has, here at least, worked out very well.
Yeah, fantastic that you guys could build that relationship. I think that's something data scientists should think about more, or at least certainly a step to success for them. I also, from what I understand, think you guys have a pretty interesting take on deployment as well. Could you share how that works from the work you do?
Essentially, everyone has their own definition of a data scientist. Mine is somebody who's good at both engineering and statistics. So I look to have people on my team who could also get a job on the engineering side if they so desired, but also understand machine learning and statistics and, everything that's necessary to do production level data science. With that being said, the way that we do deployment is that we have what's called Aloha as our layer between the engineers and the data scientists. So Aloha is an open source project. You can check it out on eHarmony's public GitHub page, eharmony.github.io. What it is it's a feature representation and model representation DSL written in Scala. So if you're familiar with PMML, you could think of this as almost like a competitor to PMML, with the big advantage in that it represents the features as well. Aloha exposes an interface that's just a function that goes from type A to type B that's called model. So the engineers provide your type A and immediately get back type B and are unaware of the implementation. The data scientists are unaware of how many times the model needs to be scored and whether or not, it goes down in production or they need, more resources in production, whatever the case may be. And they're just interested in providing the optimal implementation to go from type A to type B. So a concrete example would be Affinity, where your type A is what we call a match proto. So we use a lot of protocol buffers here. And your type B is a double, indicating the probability of communication. We have a service called model service, where the data scientists upload different Aloha model implementations for Affinity. And then the engineers have something called scorer service, where they go and download from model service the implementations, instantiate them, and then accept requests from other services within the business to score particular users. So they'll say, a client of scorer service will say, I have a match and I want to score it for Affinity, and scorer service will return back a double. And so what this allows is a separation of concerns, where the engineers and the data scientists can really move at their own speed. And this has made our lives on the data science side so much easier, because we can have an idea and get it all the way to production without even telling the engineers. As far as they're concerned, they just have a new implementation. We haven't changed our types A and B. We've just changed what the function actually does. This has just made it so that we can change things up. We can try different models. We can, I'm in the process of trying some nonlinear models, some GBNs and some random forests as well. We just stick that stuff right in production. And because everyone on our team can write production level code, we have a trust between the engineers and the data scientists that we are not going to create a function that takes 100 times as long to evaluate. And if we do, the onus is on us. And, we have safeguards to prevent against that.
And then is your, let's say, are you able to sleep at night because you've done validation on your model, or do you have some sort of production checking as well?
I'm able to sleep at night. I do a lot of validation. So when we train our model, we don't just go ahead and look at the training set and create an Aloha model. We, after that, do various levels of validation where we make sure we can instantiate the model we made. We make sure that the Aloha model and the native model, like the VW model, produce the exact same results. We then do some load testing to say, okay, the Aloha model evaluates, takes this long to evaluate. We also push a number of statistics on the model to Graphite, testing statistics on some holdout set. That these are reports I can look at every day. And then we have it fails fast. So our model trainer process will fail immediately if a model can't be deployed. Because at the end of the day, if we miss a day for deployment of a model, it doesn't bring down the business. The next day, it's not as good as it could be, and that'll be fixed when we come to business the following morning. So we really have it set up such that we don't need to carry a pager. We don't need to have be woken up in the middle of the night because we're sure our models work, or else they don't go to production.
We touched on earlier Face Parts, which is an interesting open source project, and of course just mentioned Aloha. Anything else interested listeners should follow up on?
So we are open sourcing. We just started another project called Spots, which is a hyperparameter optimization framework written in Spark. So we make a lot of use of Apache Spark here. And what we found was that there exists a number of hyperparameter optimization frameworks, probably one of the most famous being HyperOpt, but there's also stuff like AutoWeka. The ability to do hyperparameter optimization relieves a lot of burden from the data scientist, but we didn't find anything that worked in Spark. So since we make use of a lot of Spark here, we wanted to release a general purpose hyperparameter optimization framework targeting Scala and Spark. So it's very young. The developer who's working on it was working on it for a little bit and is coming back to it hopefully next week. But it's up on our public GitHub page and you can follow along the progress there.
Awesome. I'll mention all those in the show notes for anyone who wants to take a deeper look. You guys hiring or anything else to plug?
We're always hiring. I'm always looking for essentially two types of candidates. Your more generalist candidates, which is somebody who can do everything from production level Java and Scala to implement VW models. We're looking at H2O, Hexadata's H2O as well. And then we're also looking for what I'm calling more specialists, which are people who are very, very good at either image processing or text processing and can come and provide general feature extraction libraries for use across all of our models. So we're looking for both types of people.
Very cool. Well, Jon, it's been great talking to you. Any place people can follow you online, Twitter, a blog, anything like that?
I am on Twitter. I'm not very active on Twitter. And you should check out, I publish a lot of stuff to eHarmony's public GitHub page. I'm also going to say I'm the host of the LA Machine Learning Meetup. So if you go to meetup.com and look up LA Machine Learning, we have meetups a couple times a year at eHarmony. We have an upcoming speaker from Hulu who's going to talk about his new deep learning-based recommendations paper that got accepted to ICML this year in July. So if you guys want to come check that out, that would be awesome. We're always looking for speakers for LA Machine Learning. So if you think you have something that's great to talk about, maybe something that's open source, I'd love to hear from you about that. That's about it.
Awesome. Well, I plan to see you in July, if not sooner. Thanks again for doing this.
All right. Thanks. Have a good one, Kyle.
You too. Take care.
For more on this episode, visit dataskeptic.com. If you enjoyed the show, please give us a review on iTunes or Stitcher.